Hello guys, welcome back to another video. In this lesson, we are going to learn about the kinetic molecular theory and the four characteristics of gases. So before we get started with that information, let's just very quickly go over the properties and the states of matter. So we've already talked about solid, liquid, and gases. We also talked about how solids tend to have those particles that are vibrating in place. Liquids have a little bit more energy and they are able then to slide past one another. And then with the gases, they have random motion. And their space between the particles is much, much larger when compared to liquid and solids. So here at the bottom, we have just the increasing of the motion / kinetic energy of the particles. And of course, as we increase the motion and the distance between the particles, the force of attraction would decrease. So the force of attraction is highest with our solids, lowest with our gases. So with that in mind, let's start focusing just on gases because that is really what we're going to be looking at in the next couple of lessons. So let's talk about the first characteristic of gas. Gases have, as I mentioned, very rapid, constant motion. And those particles are going to be colliding with each other and with the walls of whatever container they're in. And if you're thinking, well, what about gases that are like in the atmosphere? They're still interacting with other particles, right? Other gas particles. They may not be within a container, but they're still having that constant rapid motion. The second characteristic of gases is that while their motion is random, they still regardless travel in straight lines. And the pathway that they follow is only going to be interrupted by colliding with another thing. And that could be, again, a particle or the container itself. The third characteristic of gases is that they will fill up all the available space if they're inside of a container. So when we think about a solid, for example, you place a solid inside of a beaker, the solid stays at the bottom, right? Gravity. And because those particles are very attracted to one another, they're going to stay together. When it comes to a liquid, it might take the shape of the bottom of your beaker, but it still won't expand up unless, of course, you put more liquid in it. So when we talk about gases, of course, you would have to trap them in the beaker or whatever container you're talking about. But regardless, the gases are going to expand and take up as much volume of that particular container as possible. So they fill up the container. The fourth characteristic of gases is that gas pressure is a result of all of those collisions that are happening simultaneously colliding with the object. So we're going to talk about pressure and the different ways we measure it in just a moment, but just know that because these gas particles are having constant motion and they're moving a lot, right? They are applying some pressure onto the container. And of course, they're colliding with one another, so there's going to be that constant collision. So with those four characteristics, let's now move to the kinetic molecular theory because we need to understand how gases behave before we can begin talking about kinetic molecular theory. And from this point on, I'm just going to talk about KMT because that's really just the way how we abbreviate that. So the kinetic theory of gases has four different sections to it. So the first is that the particles in the gas are considered to be very, very small. Like hard spheres with an insignificant volume. Now, of course, we know that they're not perfect spheres, but we are going to be talking about how the particles are really, really small and that they are solids, right? Because we are talking about atoms and different compounds. But regardless, their volume is going to be insignificant. So they're just going to be very, really, really small individually. Okay. So the second part of the kinetic theory is that gas particles exert no force in each other unless they collide. So let's talk about these two particles we have here in the screen. Let's just see that how they're both on different sections of the screen. So right now, at this point, there's no exertion between the two. So they're not interacting with each other, and therefore they're not pushing or pulling each other. They're not colliding. So there's no force being applied from one to the other. However, the moment that they collide, now there's going to be some sort of interaction, and at that moment of collision, the applied force. And usually that force is what's going to cause that direction change of those particles that otherwise would be moving in a straight direction. So the third part of the kinetic theory of gases is that the motion of the particles in a gas, again, is rapid. It's constant and it's random. So just like we mentioned, one of the characteristics, it shows up again in the kinetic theory. So we're saying we're not necessarily able to 100% predict how a particular particle is going to behave, because at any given point, it can have that interaction with other particles or other containers that might change that random motion. So the fourth kinetic theory, or fourth part of the kinetic theory of gases, is that all collisions between particles in a gas are perfectly elastic. What do I mean by that? Let's look at the visuals here. Elastic means that when the two interact, they collide, but they go their separate ways. So, like again, it goes back to the force. Two particles collide, and during that interaction, they just go their separate ways. They don't come together. They don't stay together. So that's elastic. But for inelastic, when we talk about that, is that they collide, there is an interaction, and they stay together. So again, kinetic theory of gases states that collisions between particles within a gas are elastic. So they're going to collide, go their separate ways. So in this unit, we're going to be focusing a lot not just on the gases themselves and their characteristics, but also the different variables that we can modify to affect the behavior of gases. So one of them is going to be kinetic energy, temperature, right? And as we know from previous lessons, the more kinetic energy a particular particle has, right? And we measure that through the average kinetic energy, which is temperature, we'll be able to start making predictions about, well, if gas particles have a lot of energy, right, and we give them even more energy, then how is that going to affect them? So for example, right here I have a visual. We have a particle that is moving, and we're assuming that that's a temperature at 10 Kelvin. So what would happen if we were to increase or decrease, right? So let's look at this example. Let's say that we were to increase the temperature to be twice as much. Well, if we increase the temperature, then that means that the average kinetic energy of the particle increased, meaning it's going to be moving way much faster. And in later lessons, we're going to figure out, okay, what is that relationship? Is it doubling, or is it, tripling, or whatever? So we're going to be looking at those, but these are questions that I want you guys to start thinking about, because that's how we're going to be analyzing some of the upcoming lessons. Now, when we talk about temperature, we're talking about the measure of average kinetic energy. And for the average kinetic energy of matter, that's, again, something that we've already learned. And in this unit, we're going to be talking about specifically temperature being measured in kelvins. Now, when we talk about the kelvins, it might be a little bit different because they're not usually the ones we use, but they are the ones that are commonly used in science, more so internationally, not just here in the US. So we will have to do eventually some calculations, but as you can see here on the right side of the screen, the relationship is adding 273 to any degrees in Celsius. So we will look at these calculations later on. Just know that that is a conversion factor that we're going to use, adding 273 to degrees Celsius and vice versa. Now, question, what is the relationship then between Celsius and Kelvin temperatures and scales? Well, that's the nice thing. Even though we use different numbers to measure, so like, for example, here on screen, we have two thermometers, one with Celsius and then the other one with kelvins, we can see that regardless, their increments are by 1. So, for example, water will freeze or melt at 0 degrees Celsius, and it will melt or freeze at 273.15 kelvins. Well, if we were to add 100 degrees, either Celsius or Kelvin, we would then reach the boiling point of water. So, 1 degree increase in Celsius is the equivalent to 1 degree increase in Kelvin. It's just the starting values that we give to each is completely different. And that is the 273 that I was talking about in just a moment ago. So we will again go look into these equations later on in the lessons. And of course, if you do have your STAR reference sheet, you will see a section that has the constants and the conversions, and that is stated there, so you don't have to memorize this value. So let's go back and talk about pressure. So definition for pressure, we have it here on screen. The force per area when gas molecules collide with each other, right, themselves, or against the sides of a container. So again, pressure is all of those collisions happening at a given moment in time. All of those collisions, they are hitting the container, they are applying pressure, right? They're hitting it with force, and that measurement of that force of collision, that is what we call pressure. And there's a lot of different units that we can use. We'll look at them in just a moment. But the standard one that we will use in this class and in this lesson and from here on is going to be atmospheres. And we've learned about that before when we talked about the normal standard, the normal melting point and normal boiling point. So we're going to be talking about atmospheres again. And just as a standard is going to be 1 atmosphere is the pressure at sea level. So here on screen, what we have now is all the different conversions that we can use for pressure. And again, we're not going to do the math just yet into the big, larger equations because we will be looking at a lot of them in this unit. But for right now, for example, if I was to say there are a total of, 2 atmospheres, how many of the mmHg, so those are torrs, or kilopascals or psis would that equate to? Well, you would just multiply 2 times all of those values. For example, also, if we had, 3,000 kilopascals, well, you can still take those 3,000 kilopascals and convert them into any of the other conversions that we have here on screen. So they're all equivalent to each other, but the one that we're going to be mostly focusing on is going to be atmospheres. But can you be given any of the others in a question? For sure, definitely. All right, so let's very quickly talk about the concept of pressure. So like I said, it measures the force of particles hitting the containers per unit area. And here in the US, we focus a lot on PSIs. But let's just think about it. We learned before that the longer the arrows of a particle, the more kinetic energy it contains. And that's just a visual representation of energy. Longer arrows, more energy. So think about the behavior of these particles. In scenario A, they have a lot of energy, which means that they're going to be moving fast in very random motions, and they're going to be hitting the walls of that container with a lot of force. Whereas in scenario B, we have shorter arrows, and what's going to happen with them is that they're not going to have as much energy within. So while they're still going to be hitting the walls of the container, they're not going to do so with as much force. So the question then becomes, which one has more pressure? Well, if pressure is the measuring of that force, right, of that collision with the container, then we can assume then that scenario A has a higher pressure because they're hitting the walls not just more often, right, because they're moving faster, but also with a lot more energy. So as we move forward with our lessons, we will continuously go back to the kinetic molecular theory, and also we're going to talk a lot about those characteristics that we covered at the beginning of the video. So in later lessons, as I mentioned, we are going to learn about the gas laws, which there's 4 different ones, and also the combined and the ideal gas laws. Thank you guys for watching. This now concludes our video.